everyone, welcome to the first lesson for topic 4.5 Energy, Work and Power. So this is the fifth topic in our M1 syllabus. It's also the last chapter as well. Okay, so for today's learning outcome, we are going to focus on the concept of work done. So we need to understand what is the definition of work done, how to calculate work done if let's say there's a force that apply on a certain displacement. Okay, so the situation that we will be encountered is that either the force and the displacement is on the parallel direction or they are in a different direction, then we might need some knowledge in resolving forces to help us to solve it. Okay, so let's start with the notes. Okay, so when we talk about the word work, right, it's pretty near to our life. So we talk about whether this time work for you or not, whether this thing or this method works for you or not, or it's an action that every adult need to do so that they can earn money and to support their life, right? So it's like everyone is working. So, but in mechanics, right, work has a very specific meaning that you might need to get rid of those idea for works beforehand when you try to understand it. Okay, so in mechanics, work is done by a force. Okay, so remember this idea. So work is not done by a person. Okay, it's done by a force when the force causes an object to move. So there's two main components in the definition. The first one is there must be a force. The second one is what the force is doing is that the force must cause an object to move. So if let's say there's a force exists, but the object doesn't move, which means there's no work is done. Okay? So for work to happen, we need a force that causes motion and we need the motion to occur. So basically go back to what I mentioned just now. So we need the motion to occur as if there must be a displacement take place. Okay, so before we talk about the definition of it, let's try to look at this new word which is called as the line of action of the force. So the line of action of the force has the same direction as the force and includes the point of application of the force. Okay, so let's try to look at this simple diagram here. So which means if let's say there's this person or there's like anything, an animal or what. So yeah, a person that's trying to push this box, right, towards the right hand side. So as you can see, what happened here is that there is a force F Newton is trying to move this object within a distance of D along this line of action. So the line of action as if this is the point where the person apply the force, right? So when it applies, so the force goes into this direction. So that's why the displacement, the distance that traveled by this object must be along this line of action. Okay? So the amount of work done by this force is denoted by the symbol W, and it's simple that W is equal to the amount of force that you apply and how far the distance of this object move. So W is equal to ms. Sorry, I should write D instead. Okay, so distance D. So W is equals to F times D. Okay, so why is it so important when we talk about along the line of action is that we need to make sure that when we apply this formula, right, the direction of the force and the distance must be parallel. Okay, so let's try to talk about an example if let's say it's not parallel in our previous chapter when we talk about forces and equilibrium, right? Isn't it we attempt those questions like for example when you try to use a rope to pull this object. So you can see this is your line of action of a force. But when you try to pull it, right, then what happened is that this force actually moved towards this direction. Am I right? So that's why you see this distance is not along the line of action of the force. So that's why we cannot straight away use W equals to Fd. So for this case, which the direction of the F and the D is different, then we are going to look at it in the second part of our lesson, which we will need to do some of the resolving. Okay, so the unit of work is F times D, right? So that's why F is Newton. So the unit for force is Newton. The unit for distance is meter. Okay, so Newton meter. But you find it's like a little bit similar with what we have previously when we talk about momentum. That's like Newton second. Okay, so when we talk about work, right, it's a bit similar when we talk about energy. We're going to explore that part in the next lesson. So there is a new, I mean, it's not like a new, but they actually created another unit to actually replace the unit for Newton meter. They are actually the same thing, but it's just that when we normally when we try to write, we will use the formula of joules. Okay, so it's denoted by J. Okay, so note that something, this is some notes about the formula here. So note that the distance moved here has been represented by D here. So that's why do us, I mean, why do we use the idea for D is that it's distance. So we are not talking about the displacement, okay? So when the motion is in a straight line and in a constant direction, the distance moved will be the same as the displacement, am I right? So if let's say we are not talking about the case where the object changed direction, then the distance and the displacement in is the same. Then which mean in another words, you can also write this formula as W equals to Fs. But I don't actually recommend that much of this, but is to just let you to understand that the idea that we are thinking of is always distance. So there's no like positive direction and negative direction involved. Okay, so yeah, that's the idea of it. Okay, so this go back to the equation that we have. So work is only done when there is distance involved. Okay, so if let's say there's no motion, the object didn't move, it means zero work. So for example, when you look at these two pictures, so if let's say this is like a wall, so this person is trying to push the wall. You see, I mean, when you try to push a wall, then you're really like pushing it like very hard. So there might be a lot of so-called effort that this person put in to push the wall, but the wall doesn't move at all. So that's why the work is actually zero in mechanics. Okay, same thing when we talk about this weightlifter. So we are not talking about the situation where he actually raise the weight from the ground to the top of his head. We only talk about he just maintain the weight at this position. So that's why there's no distance involved as well, which means it's zero work also. Although he actually used some effort to actually maintain in this position. Okay, but in physics, we talk about the work, it must be having distance involved. Okay, so work is a scalar quantity. So as what we mentioned just now, it's F and D. So D is like a scalar quantity. So and some part of like uh much more detail, much more complicated explanation that they put in is like work is actually like a scalar product of two vector, but we are not going to explore that part. So because you doesn't need that in your syllabus and I don't want to confuse you guys, but just remember that work is a scalar quantity, but that something special is that it can be positive or negative, but otherwise it has no direction. Okay, so I'm going to explain this and further when we talk about the example later. But what is important is that I want you to remember that work is a scalar lah. It's not a vector, so it doesn't indicate to you any direction. Okay, let's look at three very simple example. So a boy used a constant force of 250 Newton to push a box. So that's like the box. Okay, so he's trying to push it. So with a 250 Newton. So push a box for like 4 meter, okay, across a floor. So the work done by the force, okay, so this is very straightforward. So the work done is equal to the force multiply the distance. So that's why 250 Newton multiply 4 meter, and that gives us 1000 joules. Okay, so number two, a girl holds a mass of 20 kg above her head. So find the work done by the girl. So remember, so what we talked about just now. So if let's say this girl is trying to hold the box of 20 kg over her head, but there's no displacement. So it's just the position of holding. So that's why the work will be zero. Okay. So the idea is that there's no distance or like there's no motion involved. Okay, so let's look at number three. So a ball of mass 0.05 kg falls a distance of 1.5 meter, find the work done by the weight. Okay, so this is the ball. So force a distance of 1.5 meter. So that's why in the definition just now I mentioned, you must remember that work is done by a force. So it's not done by a person or something like a force that you're trying to push it or pull it. So for example, like the weight, right? So weight isn't caused by a person or yeah, something like that. So it's just basically a force. So that's why you need to understand the idea of it. So even things like normal reaction can cause a work done as well. If let's say it's in the direction of parallel to the direction of motion, but that's like quite rare lah. But my main point is that work is caused by a force. Okay, so this ball force a distance of, so that's why we need to get what is the force, right? So the force in this question is actually the weight. So how are we going to get the weight is from mg. So the weight is equal to 0.05 g. So that's why that will give us 0.5 Newton. Okay, so that's why work equals to the force multiply the S. So which means we have the force, which is the weight is 0.5 Newton, multiply the displacement or the distance 1.5. Sorry, I should write D. Okay, so it will be equal to 0.75 joules. Okay, so that's the idea of it. Okay, so let's look at the very short part of the notes before we attend to the question 4 and 5. Okay, so the first thing in the third question just now, you see the words work done by the weight, right? So sometimes in a question, this work done by the weight can be referred to the work done by the gravity, okay? Because we understand that why there is weight in this world, right, is actually caused by the gravitational acceleration. So it's actually caused by the gravity. So work done by the weight is actually the same thing when we talk about work done by the gravity. Okay. The second thing is in a question later you will see the word against. Okay. So yeah, when you look at the question 1, 2, 3, right, you realize that how they mention this question is in a form where work done by the force, work done by the girl, work done by the weight. So which means it's always like work done by something. So which means that these are the work that actually cause the motion to happen. Okay? But then in real life, we know that, when we talk about normal reaction or when we talk about friction, yeah, specifically. So friction is the force that actually opposes the direction of motion. Am I right? So that's why if let's say there's a resisting force that opposes the direction of the motion, right, then the work done of this force will be negative. Okay? So we say that this work is done against the force. Okay, let me give you an example. So, if let's say this is an object, let's talk about an easier one. So, when you talk about if let's say you try to pull this object, so the work that, because when you try to pull it, so which means the direction of the box is moving towards the right hand side, right? So that's why when you try to pull the box, it actually helps you to move this object. So the motion is aligned, is parallel, is in the same direction on where the direction of motion happened. So that's why the work done will be a positive number. Then if let's say there's like friction, then this friction will be opposing, right? It's in the opposite of the direction of the motion. So this work done will be negative. Okay? Then we always talk about the idea where the work done is negative because of you have a negative F, because the F here is not in the direction of the motion. So we try to avoid the idea where we talk about it's a displacement. So going here is positive, then going there is negative because it's still a scalar there. So the work done by a friction is normally negative because you can imagine work done is definitely going to opposes the direction of the motion, right? So if let's say we have a negative value, so in another words, if let's say we try to change it to positive, then how are we going to express that? Is that we will note it as is the work done against the friction. Okay, so the idea is that I hope that you understand that when we try to use the word against here, it's not the same thing when I try to say that it's like against this force. But the against is just that the force is like against the direction of motion. So that's why if you didn't, if you are writing like work done by friction, then that will be negative. If you write it as work done against the friction, then it will be positive. Okay, so just like that. Okay, then the next term that you'll be seeing is non-gravitational resistance. So it seems like a very, high level of language, yeah. But the idea is pretty simple. So you can see non-gravitational. So it's the resistance, right? So that's why this refers to all the component of forces that act against the motion. So which means all these forces is trying to avoid the motion to happen. So except the gravity. Okay, because from the term itself, you can actually read it like non-gravitational, right? So that's why it's the resistance that beside the gravity. So what are the example? Then it can be like the one that we are pretty familiar with, like the friction, or the thing when we talk about air resistance, we are not so, we didn't actually study this for a very detail, but the idea of it is like it's pretty similar to friction law, so which means it's all the force that trying to resist the motion. Okay, so yeah, then the last thing is if let's say we were to calculate the work done. So if let's say there are several forces act on a body, we can add all the work done by each force to get the total. So how are we going to do that is that you can imagine that all your work done, it will have this positive one, which is in the direction of the motion, or the negative one, which is in the negative direction of motion. So that's why for all the force that create a work done that's like opposing the direction of motion, we say that the work is done against the force, right? So when we calculate the work done, then it will be the work done, sorry, let me try to write properly. Okay, so which means that it will be the work done by something. Okay, so which means you try to add them up everything for the one that is like in the direction of your motion, right? So this is the part where contribute to the motion of the object. So this is like help the object to move. Okay, or in another words, it's in the direction of motion. Okay, and then after that, you are going to minus off the work done that actually opposing the direction, right? So work done by, you will minus off the work done against. Okay, so when we talk about work done against, meaning that it's already in the positive form, yeah. So we are not doing like negative equals to positive. We are doing like so which means, for example, if you try to pull it, the work done is 60, then the friction is 50. So which means the work done here will be 60 minus 50. Okay, so that's the idea of it. So the work done against the force, then it will be the one that opposing or avoid the motion. Okay, avoid the object to move, avoid the motion lah, yeah. Then after that is opposes the direction of motion. Okay, so that's the idea of it. So now we'll be looking at two more examples before we talk about the part where the direction of F and D is not parallel to each other. Okay, so let's look at example 4. A ball of mass 0.05 kg is raised through a distance of 1.5 meter. Find the work done against the gravity. So which means this ball. Okay, so the mass here, or it's like the weight here, will be 0.05 g. Am I right? But this thing is actually raised upwards through a distance of 1.5 meter. So you see, when they ask the question, they say that find the work done against the gravity. Why is that so? Because gravity is basically in the opposite direction of the direction of motion. So that's why if let's say it's the work done by the gravity, then you're going to get a negative answer. So when we are trying to do it as work done against the gravity, then you are just going to negative your negative answer. Okay, so we are going to write a full one so you can understand when you try to do revision in the future. So you can see that the weight is opposing the motion. Weight opposes the motion. Okay, so let's try to find the weight first. So which means the weight here is equal to 0. let me write full because later W is the same. So weight is equal to 0.05 multiply 10 for the gravitational acceleration. So that gives us 0.5 Newton. Okay, so when you have this kind of question, so just assume that it's the same thing like how you do the work done by the gravity. So the work done by the gravity, because of the force in the negative direction of the, it's opposing the motion, right? So that's why it's negative 0.5, and the total distance take place here is 1.5. So from here we can get negative 0.75. So since the question asks the work force against, right? So that's why the work force against the gravity will be negative negative. So that's why that's going to give us positive 0.75 joules. Okay, so I hope that you can get this very simple idea. Okay, number five, an object of mass 40 kg is pulled a distance of 5 meter at constant speed along across a horizontal rough ground by means of a horizontal rope. Okay, so which means that you can imagine that's this horizontal rough ground. Okay, so the object of the mass of 40 kg, so that's why the weight is like 40 g or 400. So it's pulled a distance of 5 meters. So I'm going to write like this. So at the end, the object maybe is here. Okay, then the distance is like 4 5 meter. Okay, and then we have this is actually pulled by a means of horizontal rope, so that's why it's actually pulled by a tension. Okay, so the coefficient of the friction between the object and the ground is 0.3, so there's a friction here which is F. Okay, so find the work done by each of the forces acting on the object and calculate the total work done. So that's why you need to make sure we label, we label all the forces here. So we have the tension, the friction, the weight, and don't forget you still have a normal reaction. Okay, so we are going to find all the stuff here. So for us to solve the W, we need to have the force, right? So in this case, we might need to get our tension first. So how can we do that is that they are telling us that it's not accelerating because they are moving in a constant speed. So that's why it's in equilibrium, that the T should be equate to the F here. Okay, so that's why we might need to find our normal reaction first so that we can use F equals to mu R to solve our tension. So in this case, there's no other force. There's no resolving involved yet. So the normal reaction is just equal to the weight, which is 40 G, which is 400 Newton. Okay, so after we got this, we also know that the tension is equal to the friction, right? So the friction is mu R 0.3 multiply R, which is 400. And that gives us 12, 2, 1, 2, 4, 120 Newton. Okay, so after we got this, then now we can try to find out. So the work done by the tension, okay, we use the word by because it's in the direction of the movement, right? So that's why the work done by the tension is equal to the tension multiply the distance, which is 5. Okay, and that gives us 600 joule. Okay, so now let's continue. So maybe we can try to do the friction. So you can see the friction is actually against, is in the other direction of the motion, right? So we should use that W against the F. Okay, W against the friction, it will be equal to the frictional force. So since you use the word against, so you don't need to denote negative here already. So the friction is the same with the tension, so which is 120 times what is a distance? Yeah, that's 5 as well, right? Okay, so remember they are not talking about the direction, yeah, so which means that the friction is here, but the displacement is like 5 meter, the distance is like 5 meter, so it's just going to be give us the same thing, which is 5, so 600 joule. Okay, then after that, let's talk about the vertical component. So what is the work done by the weight? Any idea? Yeah, so in this case you can see that, is there any vertical motion? That's no, right? So that's why in this case, this force doesn't create any motion. So it's 0 joule. So it's the same thing the work done by the normal reaction is equal to 0 as well. Okay, so that's the idea. So now let's try to solve the part for the total work done. So total W will be equal to all the total done by the force. So that's why in this case, then we have the 600. So since this is 0, 0, then we can just, eliminate it. So we need to minus off the work done by the 600, right? So that's why minus 600, and that gives us 0 joule. Okay, so that's the idea. So which means, at the end, that's actually no work done. Okay, for the second part of the notes, we are going to discuss the situation where the direction of the motion is in a different direction to the line of action. Okay, so like the situation that I mentioned just now. So for example, if let's say you try to pull this object with a certain angle to the direction of the force, right? So which means this is your line of action, but then the displacement take place is actually a horizontal component. So that's why you will need to do some resolving here because they are not parallel. Okay, so we know that only the component of force in the line of action counts towards the word side completely, like all of the force. So if let's say you try to when you try to pull something towards this direction, right? So, okay, maybe let's try to talk about the situation if you are using the same F. So, which means the force that you apply here is 50 Newton. The same thing here, the force you apply here is 50 Newton. But only the force that is parallel to the line of action will actually contribute completely and counts towards the word. So, which means that in this case, then the force that actually caused this object to move is actually smaller than 50. Okay, so because we know that when you try to resolve it, then this is how we get 50 sine something, right? So when you sine theta, then it's going to give you a number that's like 0 point something. So when you use 50 times that, it's going to give you a smaller value. Okay, so now let's try to look at it and try to just derive a formula out from there. Okay, so which means in this case, what is the force that we have when we try to resolve it into the x component? So which means in the vertical direction, in the horizontal direction, then you will realize that this is basically the force that you apply is equal to the F cos theta, right? So you should be pretty familiar with this already. So this is the angle that touches the component. So F cos theta. So when we try to calculate the work done, then it will be equal to the force here is F cos theta and then multiply the distance, right? So it will actually give you, we can try to, because this is just multiply and their relationship is all multiplication. So we are just going to rewrite it in a better form, which FD times cos theta. Okay, so you can see that I note it here. So although it's a vertical component of the force, so which means when I try to resolve it, then in this direction you can get Fx, right? In this direction, you can actually get Fy as well. And this is not 0, right? Because if let's say this is 50, then this is going to be 50 sine theta. But the idea is that you see when you're trying to look at this force, so it's not going to contribute anything because when you try to talk about work done, there must be a displacement taken place. So which means there's actually no movement in the vertical component. So that's why it actually doesn't work. So in another words, it's actually no work done by this resolved component of F because there's no vertical displacement that take place. Okay. So in a conclusion, so when a force of magnitude F Newton move a body a distance d meter at an angle theta to the direction of the force, then the work done of the force is just W equals to force multiply d and then cos theta. Okay, so now let's look at two more examples, then we'll end this lesson. Okay, a packing case is pulled along a horizontal ground a distance of 5 meters by means of a rope inclined at 60 degrees to the horizontal. Okay, so that's this horizontal ground. So the packing case, okay, is pulled by the means of a rope inclined at 60 degrees to the horizontal. All right, the tension of the rope is 100 Newton. So the total distance is 5 meter. Okay, so find the work done by the tension. So W is equal to the equation just now. So F times D times cos theta. Okay, so the force here is 100 for the tension, then D, the distance is 5, then the angle here 60. Okay, so from here then you'll be able to get your answer 250 joule. So you can see that if let's say it's not along the line of action, right? So that's why the work, or it's actually the force that it actually contribute to the direction of motion is eventually smaller. So that's why the work done will become smaller as well. Okay, so question 7. A box of mass 25 kg is pulled along a slope incline at 15 degree to the horizontal. So this might be a little bit more complicated because we are talking about an inclined plane now. Okay, but the idea is just the same. Okay, so this mass is 25 kg. So we have this box on the slope, right? So 25 kg, so it tells us that there's a weight of 25 g. Okay, so it is pulled along a slope by a force of 100 newton, so that's why the force going up is 100 newton. Okay, so the slope is inclined at 50 degree. So at the same time, we know that there will be normal reaction, right? That's like perpendicular in the direction perpendicular to the slope. So when you try to extend it, then this is how you get 15 degree. Okay, so the non-gravitational resistance, so which means the friction and so on, is 5 Newton. So it's opposing the direction of the motion, so which is here. Okay, so it's 5 Newton. Okay, so the box move a distance of 4 meter up the slope. So which means that, let me just write here, the total distance that take place is 4 meter. Okay, so we need to find all the work done by all these forces, then after that calculate the total work done. Okay, so for A, the work done by the 100 Newton pull. Okay, so you can see that this box is definitely going to move along the slope. Am I right? So that's why the box move a distance 4 meter up to the slope. So this force is actually in the parallel, is the same direction with the motion. So you don't need to do any resolving. So it's just that W equal to the force, which is 100 multiply 4. Okay, and we can get 400 joules. Okay, then after that B, the work done against the non-gravitational resistance. So the word against, so which means it indicates to you that this work done is actually opposing the direction. Am I right? So that's right, because the friction here is eventually avoid the motion of this box. So in this case, then the work done against the non-gravitational resistance. So let me just write NGR. Okay, it will be equal to our 100. So sorry, the force is 5, and then the displacement is same as well, so 4 meters, so it's equal to 20 joule. Okay, so simple as that. Then after that, C, the work done against the gravity. So work done against the gravity. So it's the same thing because gravity is opposing the direction of the motion as well. So that's why they use the word against. So W against the gravity, which is G. So in this case, there will be the weight. Okay, so you have like two things that you need to resolve, right? The first one is whether you resolve it in the direction here or you resolve it in the direction here. But you can remember, like previously we said that if let's say it's perpendicular to the motion of direction, it will actually give 0, because in this case then the line of motion is actually towards this direction. So the displacement that take place is eventually in this direction also. So that's nothing to do with the perpendicular direction. So in this vertical direction, there's no displacement take place. So that's why there is no work done. Okay, so now let's continue. So which means in this case, the work done against the gravity, that it will be, we will need to resolve it into this direction. So that's why the force is 250, then sine 15, right? So towards this direction, we are resolving here now. Then multiply the displacement, which is 4. Okay, so from here, then we can get the answer as 258.89. Okay, and we try to just make it to 3 significant figures, so 259 joule. Okay, so I hope that you can get the idea. So basically, every time when we're trying to see, it's just that the direction of the displacement taken place, then you are just going to put in the force that is in the along the same direction, then you can get the answer of it already. Okay, so yeah, D. Okay, when we try to look at D, then maybe you can understand it further. So you see, right, we need to find the work done by the normal reaction. So work done by normal reaction. So what you can see here is the normal reaction is perpendicular to the motion, right? So that's why actually there's no displacement in the vertical component as well. So we know that if that's the case, then that's going to give us 0 joule for the work done. Okay, okay, let me try to explain this in further. So there's like two ways that you can try to look at this situation. So the first one is that imagine if let's say I were to look at it here, okay? Then you realize that there will be a certain force here, right? So when we talk about W equals to FD, your F has some value because definitely your normal reaction has a certain force, right? That's going to be your weight and then cos 15, okay? But then if let's say we talk about the vertical component, then there's no displacement involved. So that's why that will be like F then times your 0, then it will just give you 0. The other alternative is if let's say we are trying to look at it like this. So we know that if let's say in this direction, then that's displacement, am I right? Which is the 4 meter just now. So if let's say there's like 4 meter here, but then what is your force here? So we know that it's perpendicular to this. So when you try to resolve it, like this force is not going to contribute any force towards this direction, am I right? So that's why in this case, then is the force will actually become 0. So it will give you 0. So no matter which idea that you are trying to look at it, the work done by the normal reaction will be 0. And it doesn't matter whether you write work done by the normal reaction or against the normal reaction. Okay? So the last question, E. Calculate the work done on the box by all the four forces. Okay, so remember it's the work done by that is like contribute in the direction of the motion, you minus off those against. So total work done will be equal to, so the one that in the direction, it will be just the push, right? The pull, so which is the 400 joule, then minus off the one that against, which is 20 joule, and then minus 258.89. So from here, then we'll be able to get 121.181, so 3 SF, so 121 joule. Okay, so that's the idea of the question. Okay, so spend some time to do your exercise and to understand it. So that's only like 4 questions. So if let's say you have any question, then feel free to just ask me. Okay, so yeah, that's it for today's lesson. Thank you.